Page 809, 809, 808. Okay. Find the derivative, use the derivative determine input of the graph. Okay, so this is very similar to the example problem I did. What did you get for the derivative? No, it should have been 2x minus 4. I think it's the same problem as what's in the notes. It's identical problem in the notes. Yeah. Sorry? Oh, I totally. This is right in the notes, guys. I mean, I'm surprised you guys are asking me this question here. This example right there. Did you get it down in your notes? Did you watch the video? Yeah, Sam? It's right there. It's in your notes. Same problem. Okay? Any other problems? Any other questions on homework? Okay, guess what? Today is the last lecture. Then we are done. This is it. Ever. Unless you show up in my class next year. Beta, I don't expect you to be in my class next year. Why would I expect you? I wouldn't expect you. Calc. Non-AP calc. Okay, last topic. Limits at infinity. Limits at infinity. Okay, guys, just do it. Just do it. Be careful about protection there, okay? Yeah. Sorry? Can I move the calculator? I mean, I don't know where to move it. Okay, can everybody answer the question? What can you say about what happens when x goes to infinity? Y goes to infinity? Sorry? Do you have a calculator there?
Oh, what the heck?
You need a calculator. Sorry? Well, I bet you didn't use protection properly. The 2x is probably not in protection. Oh. Beta, did you get this graph? What can you say when x goes towards infinity? What's happening to y? Staying the same at what value? Samantha? Sorry? Decreasing to where? You think so? You have a graphing calculator? Yeah, Ian. Goes closer to 1/2. Well, just do it. Get trace out there. Okay? Look at what's happening to y. Do you see it going towards 0? Sorry? It's going to 1/2. Should this be a surprise to you? Why not? Sorry? There's a 2 in the denominator, so what? Okay, this is stuff that you have done in chapter 2. How many people remember the rules there? Awesome. How many hours of sleep did you get?
A lot.
Like 3.5? Just leave it there. Thank you. Thanks. Okay, let's take a look at, let's see, where do you want to go? We want to go to somewhere like session 2.6, page 146. Oh, lo and behold, on page 148. Open sesame.
I don't know where my book is because
Oh. Okay, beta, front row, no books. No books.
I looked at my phone.
Except those people who recently immigrated from China. Always have the books, always at the top of the class.
He doesn't even understand.
I know he's not from Taiwan. Michelle, he's not from Taiwan, is he? Is he from Taiwan? Do you speak the same language in Taiwan as mainland China?
No, okay, no, I'm expert.
Okay, Henry, what's your comment?
No, so there's like different dialogues for different regions, but we all, like, Mandarin is like the official language.
Mandarin is Mandarin.
But, like,
It sounds different.
Sounds different. But people on mainland can speak and communicate with Taiwanese people? Or only the Mandarin speaking, right? Not the Cantonese speaking. Cantonese is different.
Cantonese, they normally speak Cantonese with their people, but they have to learn.
Had to learn Mandarin. Oh, okay. Didn't know
The
that.
writing's on it.
The writings, the script is the same. Okay, so what I would suggest to you is open your book to page 148 and take a look at those rules, because that's what this is based on. Okay, that's what this is based on. And yeah, it's an asymptote. Okay, it's an asymptote. It tells you right here, limited infinity is like an asymptote and behavior. Okay, so this particular problem here, okay, is based on the fact that the degree of the numerator is what? What's the degree of the numerator? What's the degree of the denominator? If they are both the same, then the limit is the ratio of the coefficients of the leading terms. Okay? Guys want me to say that again? Okay? If the degree of the... Let me write this down, okay? Probably. Some people want to read this rather than... So the degree of this is equal to 1. Degree of this is also equal to 1. If those two degrees are the same, then the limit is equal to ratio of the coefficients of the leading term. I'm assuming you understand what leading term means, right? A polynomial written with the highest power starting out with the highest power. Okay. So what's the leading coefficient for the numerator? 1 coefficient. And denominator? All right, you guys got that? All right, and you can even see it graphically on your graphing calculator. All right. Next
So the horizontal axis
is the limit. Yes. You want to take a look at the definitions of limits at infinity on page 811. All right, I mean, that's pretty simple notation. Couple of other things on the slide here. Remember yesterday or day before we talked about something like this, limit as x goes to 1 plus, right? Or limit as x goes to 1 minus. You know the difference between these two, right? What does 1 plus mean? Going, well, it's going from the right, not to the right, but from the right of 1. Right? A little bit more than 1. This one is a little bit less than 1. So it's not going to the right, but it's going from the right of 1 towards 1. And this guy at the bottom is going from the left of 1 towards 1. Okay? Well, since we don't know what infinity is, we can't be on the other side of infinity, can we? Because we don't know where it is. So concepts like infinity to the plus doesn't make any sense at all. Because I don't know where infinity is, so I can't go from a little bit more than infinity. You guys got that? Okay? So the left and right limits are not written like this, okay? Instead, they're written like x goes to plus infinity, that'd be the right limit, and x goes to minus infinity, that would be the left limit. You guys with me? No? Okay, let's write things down then. Okay. So what I'm trying to do is make a distinction between something like this and something like this. This is the left limit. This is the right limit. Unlike these other things that I have, okay? Unlike this. Okay? In other words, the difference is here the plus is a superscript up at the top. You don't have that for infinity. All right? Okay? So if you were to look at the red thing, what I'm talking about is if you had a graph like what we have in here, this guy, then the limit as x goes to infinity is this number that we are talking about, this y value. You guys with me on that? And if the graph was doing something like this on the other side, something like that, then x to the minus infinity would be wherever this number was going. Wherever that number goes. You with me? Okay, so this is minus infinity because that's where I'm headed. Okay? And this is plus infinity because that's where I'm headed. Alright? That's not the limit. That's what's happening to x. The limit is always the y value. Always the function value. Okay, not the x value, the y value. Okay? Is everybody there? How about these two? Does everybody see this is pretty straightforward? Does everybody agree with that? Mark, you want to explain why it seems that obvious that, yeah, you won't accept it? Sorry? Yeah, but why is it equal to 0? Does that kind of make sense to you? Leah, does that make sense to you? Sharik? Exactly. Exactly. What he's saying is that if this number here, x, is going towards infinity, remember infinity is a huge ass number. Huge number, okay? And when you've got a big number here, okay, what do you think the result's going to be? Close to 0. Close to 0. Okay, and that's true for whether it's going to plus infinity or minus infinity. You guys know that there's nothing like this, right? There's no positive 0 and negative 0. It's 0. Okay? There is no sign attached to it. Why is that funny? Okay. All right? So you got to know this, okay? Limit of 1 over x is 0 as x goes to infinity. Okay. Evaluating limits at infinity. Couple examples. A few examples coming up, okay?